As we work more with functions, we start to look at the relationships between the variables that we're working with. And not all the times that we are graphing our relationships are they being a completely straight line and follow along that line. So we're actually going to be learning about something called scatter plots during this lesson that shows that there still can be linear trends, but they may not line up perfectly in a line. So let's start with talking about increasing and decreasing functions. So we know that graphs, of course, show data. But graphs do more than show data. They show relationships or lack of relationships between the two variables. So when we're graphing our data that we have, we're showing that there might be a correlation between those two variables that we are graphing, showing that as one goes up, the other goes up, or as one goes up, the other one decreases. So the graph of a linear function, of course, should be a line. And it should be a line because that's the definition of linear. We should have it going in a straight line because it's linear. So if we have a positive slope, then it means it's going to be an increasing function because they're going to be going up together. So it's a positive slope, it's an increasing function if both variables increase together, and you have this general trend of it going that way. Negative slope, of course, means it's a decreasing function, and as one goes up, the other goes down. So a negative slope is a decreasing function. As one increases, the other decreases. So you actually have this trend that kind of goes this way. So maybe this is time, and this is the amount of money I have because I'm spending it. So as time increases, the amount of money I have goes down. But then, of course, you can have kind of just this constant, almost nothing happening, and that's going to be our zero slope. So a zero slope is a constant function, and it's as one increases, the other does not change. So you're going to have basically just a steady line. So this could be water sitting in a bathtub, and if we're not doing anything with it, as time goes on, the amount of water in the bathtub just stays steady. So let's take a look at some scenarios and look at how we graph those. All right, so we have this scenario. Half-life is the time required for a quantity to fall to half of its previous value. If there are 100 grams of radioactive element at the start, there will be 50 grams after its first half-life, 25 grams after its second half-life, and so on. So sketch a graph that represents the amount of radioactive element left in relation to the number of half-lives that have passed. So I need to graph this situation. Remember, we always get to choose which axes are going to be which. Time tends to be x, so half-life, because that is actually time, will go on x, whereas the amount of radioactive material will go on y. So I've set up my graph so that radioactive material is going to be on our y, and I have, of course, it going up to 100 because that's our starting point. I have them going by tens because that's just convenient with how our graph is. Half-life, because its time is going to go around here, and they can just go by ones. So we said at the start there's 100. So at 0 time, there's 100. After one half-life, there's 50 because it even said that in there, and it's going to decrease in half. After 2 half-lives, there's going to be 25, so it's right here. Now we're at 25, so half of that for the next half-life would be 12 and a half. So for 3, we need to be at 12 and a half. Then for 4, we need to take 12 and a half and divide it by 2. So if you're not good at that yet, you of course can always use a calculator. So 12.5 divided by 2, we're at 620.25. So at 4 half-lives, we're at 625. 5 half-lives, we need to divide that in 2 again. We're at 3.12. So at 5, we're at about 3. Divide that in 2 again. 1.5. Oh goodness, this is getting really, really low. And you can probably see the trend that we're essentially slowly getting next to 0, but never truly getting exactly next to 0. So this is, if you are familiar with different types of graphs, this is actually kind of an exponential graph, a decreasing exponential graph. And we're getting closer and closer to 0. So now let's take a look at our questions. The question is asking us, is it positive, negative, or a constant function? Well, so as time increases, as time increases, the amount of half-lives are increasing, what's happening to the radioactive material? The radioactive material is going down. So if we're trying to figure out if this is positive, negative, or constant, we can look back at those things that we just wrote. If one is going up and one is going down, that's a negative function, which should make sense. The amount of radioactive material is decreasing. Our next question is it linear or nonlinear? My goodness, is this definitely not linear, okay? Because it's like, it curves down, so that's definitely not linear. This is nonlinear. So even if we have a nonlinear graph, you can still say if it has a negative, positive, or constant function. Let's take a look at another example. So here we have another scenario that we need to graph and then answer some questions about. So Kevin got a $50 Starbucks card for his birthday. He uses this to buy a coffee for his favorite math teacher every morning. Oh, that's really sweet. Sketch a graph of the function that can be used to represent the amount of money on the gift card in relation to the number of drinks purchased. Okay, so he's starting with $50, and then every morning he's buying another drink. So we need to decide what's going to go where. Should money go on Y or on X? Money tends to go on Y, so the amount of drinks can go down here. So I've set up the graph so that we have amount of money on Y, going up by 10 up to 50 because that's what we're starting with, and the amount of drinks on X. Now, they don't give us specifically how much a cup of coffee is costing here, so I'm actually going to let you choose the amount you want it to be, and then finish this up. So your graph's going to look different than all the other students, because what you might consider a cup of coffee should cost is going to be different than someone else's. If you're someone who likes to buy these extravagant cups of coffee, then you might be going down 5 every single amount of drink, whereas someone like me who's very, very happy with regular coffee, just a little sugar and a little milk hint, would be spending maybe like $2.50 each drink. Okay, so choose for yourself how much a cup of coffee costs, and then go ahead and graph this, and then I want you to tell me, is this positive, negative, or constant function, and if it's linear or nonlinear. So go ahead and take a second and finish this one up. We're now going to take a look at scatter plots, and I really like scatter plots because they really show real life situations. So we've been working a lot with linear equations, which gives us a very nice straight line. But in real life, data is not always going to run along a straight line. It's going to be kind of linear-ish, but you're going to have points kind of all over the place. Think about if you were graphing height compared to, I don't know, a grade level. You'd expect that, yeah, as people go up in grades, their height's also getting bigger and bigger and bigger. But we all know that everyone in second grade is not going to be the same height, and everyone in sixth grade is not going to be the same height. So you're not going to have a completely linear graph. It's going to be very similar linear going up together, but the points are going to be kind of spread out a little bit. So that's essentially what a scatter plot is. It's a collection of points on a graph. And once I show you a couple examples of scatter plots, the name will make sense because they can be pretty scattered. So you'll see this next term pop up a lot, and that's why I wanted to put it on your notes just so you don't freak out when you see it, because we actually know what this means. Bivariate data. Well, bi means two, like bicycle. Variate means variable, so we're talking about data with two variables. That's exactly what we've been graphing the entire year. So bivariate data is just, we're talking about dealing with stuff with two variables. Nothing new, just those terms aren't new. So scatter plots, they're used by scientists to see if two variables really have a relationship or a correlation. And correlation means there's a connection there, that somehow these two things are connected or related. This does not necessarily mean one necessarily causes the other. Okay? So just like our example before, being in an older grade does not cause you to be taller. Okay? So think about like the fact if someone skips grades, is just because they skip a grade doesn't mean they're going to shoot up a foot. Being in a certain grade does not cause you to be taller. There's definitely a correlation and relationship there. People are going to get taller as they're up in higher grades, but one does not cause the other. And same thing like with the other way. Just because you're 6 feet tall doesn't mean like, oh, you're a college student. Okay? So this does not show a causation. It shows there's a relationship or a correlation. And scatter plots, we might hear the word slope, but really they don't have slopes. Scatter plots don't have slopes. They have trends. So instead of saying something has a positive slope, you can say it has a positive trend or a positive correlation. So I've actually put some examples of this here for you. So these are kind of what scatter plots look like. So if we have a positive correlation or a positive trend, then you kind of have this positive sort of direction going on. Okay? You can definitely see that as one is increasing, the other's increasing. You don't have a straight line, that's for sure, but you definitely see that there is this positive trend that they go up together. Same thing over here. This is a negative correlation or a negative trend. As one thing increases, the other's going down. It's not a straight line, and that's okay. We still see that there's definitely a relationship going on here. And lastly, there can be no correlation, no trend. They really are truly scattered all over the place. And that it's not that this is a bad thing. If anything, this shows us data too, that whatever it is we're graphing here, there's no relationship between them. So this might be your favorite color and your shoe size. There should be no relationship there at all. There should be nothing that says that just because you like green, your shoe size should be 6.5. Okay? So sometimes you're going to see something where there's absolutely no correlation, no trend, and it will look like this. They will be truly scattered. So now let's take a look at some scatter plots and answer some questions about them. So we're going to take a look at two different scatter plots and just look at what we see. So in the instructions it says, look at the following scatter plots and answer the questions. Does it have a positive, negative, or no correlation? Does one variable cause the other? And what could explain this relationship? So let's take a look at this first scatter plot. So here we have a husband's age being graphed according with the wife's age. And we definitely see a positive correlation going on, because we have this sort of, as one increases, the other increases. So we have a positive correlation going on. Does one variable cause the other? Does a husband's age cause the wife's age? No, we can see that there's definitely a relationship. Just because the husband's old doesn't mean the wife has to be old. Doesn't mean one causes the other. And then what about this last one? What could explain this relationship? So what could explain the fact that there does seem to be this trend that as the husband age increases, the wife age increase? So we have 60-year-old men marrying women between the age of 50 and 65. What can explain that? Well, probably the fact that people are going to want to marry people who are the same age as them. So the older a person is, the older they want to marry. So in our explanation, we can say people like to marry someone close to the same age as them. And of course, there's what we call outliers. There's people out here and out here who are marrying someone a lot older than them or a lot younger than them. But the general trend, the general population tend to marry people kind of close to their own age. Let's take a look at another one. So here we have a graph of age as it's increasing and the daily amount of video games being played. So first question is this a positive, negative, or no correlation? So we have this trend that's going down. So it's looking like as age increases, the amount of time people spend playing video games is going down. So if one's increasing and the other's decreasing, then this is a negative correlation. The next question asks is, does one cause the other? So does your age, you getting older or being younger, cause how much video time you play? No, not necessarily. Just because you're a certain age doesn't mean you have to play a certain amount of video games. People are very different. So the last question asks, well then what could cause this relationship? What can be the cause of the fact that as people tend to get older, they play less video games? Well, there's a couple different things we could say. We could say that people lose interest in video games when they're older, or because it's not what they grew up with, they're not going to be wanting to play it. Or you could say that people have less time to play video games as they get older. There's a lot of different things you can say. So you can pick your favorite and write that down. I'm going to stick with the time one because as an adult, I can personally attest that I have a lot less time to play video games than I did as a kid. So I wrote that older people have less time to play video games. You, of course, can be writing the reason that you think. And I know I'm writing this on top of the graph. You can write it off to the side or wherever you have room. So now let's take a look at making our own scatter plots. So as much as I like scatter plots, plotting them yourself is actually kind of a pain. With linear equations, you need 2 points and then you can draw a line. With scatter plots, you really do need to plot every piece of data they give you so that you can get the whole picture. And there tends to be a lot of data so that you can see a trend. So I do apologize, but plotting your own scatter plots tends to be annoying. So you just have to go through and plot your points x, y, x, y, x, y. So I will go through this with you. So if we're going to be plotting this, we have the quality of headphones versus the price. So let's set up our graph. So I put quality of headphones on the bottom, price on our y, because quality of headphones comes in the first column and x always comes first. Then we need to set up essentially how much we're going to go up. So I'm looking at it, and quality of headphones tends to range from 10 to 85. So I'm thinking maybe I can go up by 10s. Then for price, so since it goes from 2 to 35, and I have a good amount of space, I think I can fit it on so that every one is 5. So now we just need to go through and do the work of putting the points on the graph. So first point is at 32, 2. So I'm going to come over here and then go up to 2. So it's about kind of right, no, actually more like there. Next point is at 10, 15. So 10, 15 is right there. So we've done these two. Next point's at 23, 17. 23 is about here. And then 17 is maybe about right there. 32, 22. Well, 32 is about here. Coming up to 22, about right there. 32, 34, so same x, going all the way up to 34. 60 and 20, so coming up to 60, and then going up to 20. 75, 23, so coming over to 75, going up to 23. Let's see, 85, 20, so 85, and then going up to 20. And then last one, we have 68 and 32, so coming over to 68, and then go up to 32. So we put the points on our graph, so that's important. So now we can take a look at just what we have going on. And we need to answer the questions if it's positive, negative, or no correlation. Does the quality of the headphones cause what the price is? And then what can actually explain this sort of relationship then? So I'm actually going to let you finish this up because you've seen me show you this 2 times. So answer for me what kind of correlation this is, if these cause each other, and then what actually could explain this relationship. And that's it for this lesson.